For my presentation, I chose to do Lesson 8, Problem 1. So for this problem, we're going to use the general form e to the v times x minus v of t over 2 alpha squared multiplied by w at x comma t. So we need to figure out our values for v and alpha squared. And as you can see from the PDE, they are both equal to 1. This means that we can set u of x comma t equal to e to the x minus t over 2 all over 2 multiplied by w comma t. We can simplify this into e to the x over 2 times e to the negative t over 4 times w x comma t. And now we need to solve for the partial derivatives u sub t, u sub x, and u sub xx. For u sub t, we get e to the x over 2 times e to the negative t over 4 multiplied by negative 1/4 w x comma t plus w sub t x comma t. Doing the same thing for u sub x, we get e to the negative t over 4 times e to the x over 2 multiplied by 1/2 w comma t plus w sub x comma t. And for u sub xx, we get e to the negative t over 4 times e to the x over 2 multiplied by 1/4 w x comma t plus w x comma t plus w x sub xx x comma t. When we plug these back into the PDE at the start, a lot of it simplifies out, and what we're left with is w sub t at x comma t is equal to w sub xx at x comma t, which is our new PDE, which is of the form u sub t is equal to u sub xx, which is what we wanted. Solving for our boundary conditions from the left side, u of 0 comma t is equal to 0, and we can plug that back into our e to the x minus t over 2 w of x comma t. What we're left with is 0 is equal to e to the t over 4 w is 0 comma t. This means that we have e to the t over 4, which cannot be 0, multiplied by w at 0 comma t, so the only way to make it equal to 0 is if w at 0 comma t is equal to 0. For the right side, it's very similar. We get u of 1 comma t is equal to 0 is equal to e to the 1 minus t over 2 all over 2 times w of 1 comma t. This means that 0 is equal to e raised to the 1/2 minus t over 4 multiplied by w at 1 comma t. And the same thing as above. This means that w at 1 comma t is equal to 0. For the initial condition, we set u at x comma 0 is equal to e to the x over 2, or is equal to e to the x over 2, and we set that equal to e to the x minus 0 for our t over 2 all over 2 multiplied by w at x comma 0 when we plug in 0 for t. This leaves us with e to the x over 2 is equal to e to the x over 2 multiplied by w at x comma 0, which leaves us with w at x comma 0 is equal to 1. This gives us our new IBVP. The PDE w sub t is equal to w sub xx. The boundary conditions w at 0 comma t is equal to 0 and w at 1 comma t is equal to 0. And the initial condition w at x comma 0 is equal to 1. Now going back, we can set a sub n is equal to 2, integral from 0 to 1 at our initial condition 1 multiplied by sine of n pi x dx. Now solving that, we're left with negative 2 cosine of n pi plus 2 over n pi. And solving for when n is even, we get 0, and when n is odd, we get 4 over n pi. So we want when n is odd, which we can write as 2k plus 1. So plugging this into our w at x comma t, you can say the sum from n equals 1 to infinity 4 over pi times 2k plus 1 multiplied by e to the negative 2k plus 1 pi squared t sine of 2k plus 1 pi x. Now, the use of x comma t from earlier, e to the x minus t over 2 w at x comma t. We can just substitute in the w at x comma t now, and we're left with u at x comma t is equal to e to the x minus t over 2 multiplied by the sum at n equals 1 to infinity of 4 over pi times 2k plus 1 e to the negative 2k plus 1 pi squared t sine of 2k plus 1 pi x. Thank you very much.